So we're going to talk about chemical kinetics. Kinetics is, whenever you hear kinetics, think energy of motion or movement from one place to another. Chemical kinetics has to do with how fast is the reaction occurring. Okay. After we get through with this discussion, we'll move into chapter 13, which is equilibrium. We do kinetics first because equilibrium, to a large extent, is based upon reaction rates. So we're going to get this one under our belt first. All right, we express reaction rates as a change in concentration. I'll just use that to represent concentration. Concentration of something. Well, okay, they're using A, so let's put an A in there. A change in concentration with a change in time. Okay, so it's like any rate. If you've had physics or if you've studied anything related to physics, velocity is a change in distance over time. So this is a change in concentration over time. And it's we usually express it in molarity. It doesn't have to be molarity, but more often than not, it is concentration in molarity. We can also express it in terms of partial pressure of the gas. If all the components in the reaction are gases, then partial pressure works also. But of course, that would give us a different value for rate, because this would be a different unit of measure. So if we were to track a reaction, such as this one, 2NO2, let's see, yields 2NO, and these are gases, plus O2. And this is always at a specific temperature, right? Reaction rates are sensitive to temperature change. So in this case, it's at 300 Celsius. And each of the components is listed here over time. When I would go from 0 time, we have a certain amount of NO2. That's our starting point. And there are no products at all at the 0 point. And it doesn't have to be that way. In this case, it is. You can start off with different concentrations. But we're going to cover a method for determining reaction rates later, called the method of initial rates. And it always starts off as reactants and no products. The reason for that is, and we'll find this out in chapter 13, is that once you start building up products, you can have reverse reaction. And they can get back together and make reactant. Okay, so if you start off initial with only this amount and study the rate at the very beginning, then this is not a problem. Concentrations of the products would not be a problem. But if we do track the reaction over time, it looks like at 50-second intervals, we measure the concentration of each one of these components. And we see that during the first time interval, right, a change in time, if it were 50 seconds, right, that would be 0 to 50, would be 50 seconds. And what's the change in NO2? Well, NO2 would be 0.01, right, minus 0.0079. Right, and that would be the change in concentration. And actually, it would be the other way around. Right? It's final minus initial. So the negative value would tell you that the rate is a decreasing amount of NO2, which is what we would expect. Another thing to notice here is that the balanced equation tells us that for every 2 of these that disappear, 2 of those show up and only 1 of those shows up. So the difference in concentration there is 0.01. Excuse me, 0.021. Right, that's the change in molarity. So you should also see appearing over here that much of NO because it's the same stoichiometric ratio. And that's what we see. And then half of that value for this one. Okay. And that all happens over that first time interval. And then we go to the next time interval, 50 seconds. What happens? NO2 reduces by how much? 14? Yeah. Now it's down by 14. And this is per 50 seconds, right? We haven't divided it in to see how much it is per second. But for 50 seconds, notice that the amount change in the second time interval is less than in the first time interval. And that would make sense because you have less of it here to complete a reaction. But the stoichiometry is the same, right? We're going to add 0.0014 to 0.21, and this is 3.5. Right? So we should get 0.0035 for NO, and half of that added to it would be O2. And that trend occurs as we go all the way down. Now these values can be plotted. We can plot them in a graph, and I think that's the next slide. Okay, it's a little hard to read, but I'll try to help out. Let's see. Get my pointer. So here's the NO2, the green curve. It starts out at this amount and 0 for the other two. Right here. And they gradually build up as you go. Of course, NO is building up twice as fast as O2 because of the stoichiometry. And then NO is decreasing at the same rate as NO is increasing. But notice that it's not a linear rate. Right? And we saw that from here. The rate of change depending on time and concentration. But we can also report an instantaneous rate. Right, so anybody had calculus? Okay, instantaneous rate, we know how to do a rate for a straight line. If it were a straight line, we just say rise over run. Right? Well, you can do that also for curves. So if you have a curve, the instantaneous rate for that curve is the tangent, the slope of that line tangent to the curve at that point. But that will change, right? If we're down here, it's a different slope. We're up here, it's a different slope. So the instantaneous rate changes over the course of the reaction. Okay. All right. And I stole my thunder. There it is in black and white and blue. Slope of the line, tangent, the curve of that. Right. The slope of that tangent line is the rate at that point on the curve. And obviously, for those curved lines, the rate changes over time. It's not a constant rate. Like a straight line would be. Correct. Right. So how do we express this? In terms, and this expression, the rate law, is exactly that. It's a law. It has no theoretical base. It has no, what's the word I'm looking for? It has no y associated with it. It's just, it has to be experimentally determined. And the rate law is an expression for this particular reaction. The rate then is equal to some rate constant times the concentration of, in our case, this reactant to some power. Right, so this will be a constant. And this will be, we're going to study three possibilities here, where n equals 0, n equals 1, and n equals 2. But experimental determination of these values should mean that it should just stab you in the back of the head. It should mean that it doesn't have to be a whole number. It could be a decimal fraction of some kind. But for convenience and for beginners, we start off with whole number, because then it's easier to describe various conditions that predominate with the different values here. And it's easier to determine the K for these reactions. Notice also for this one, we're only interested in the disappearance of the reactant. So the rate of the disappearance of the reactant will also tell us something about the products because of the stoichiometry. Right? So we really only need to study this one for that reason, and for the initial rates reason. We usually study disappearance of reactant. Okay, and this is called the order. That's the order of this reactant. So the rate law with respect to, this would be rate, with respect to this reactant is in order. If you can have other factors in here also, say if you have two reactants, you can have an N order for this one, and you can have an M order for the second one. Right? But it will only have one rate constant. We're going to look at examples in a minute. And that's the initial rate statement right there. We're studying this at the very beginning when the products are not an influence on the rate of the reaction. Right? If we start getting enough products formed, then you get reverse reaction. And that's probably what we were witnessing with that list, where NO2 and NO and O2 were products. As we built those up, then it slowed the reaction here because you were getting reverses. Okay. There we go. And like I said before, this value and this value are experimentally determined. You cannot deduce them from the overall reaction stoichiometry. We're going to find out later that these reactions, well, I erased it, but where you have this thing right here, right, reactants and products, there may be several steps right in here. This is the overall. There could be steps, mechanism steps. And those mechanism steps, we can use their stoichiometry to infer a rate law for each step. Okay, just keep that in the back of your mind. We'll get to it in a minute. But the overall reaction has to be experimentally determined. And of course, we're going to find out later that if we propose a set of steps for a mechanism, then the rate law, the overall rate law that we experimentally determine, will guide us in determining which of our proposed mechanisms is valid, because you usually propose a bunch of them and you just start eliminating till you get down to the most likely one. It's that Sherlock Holmes statement, right? You know which one I'm talking about. What do you say? If I paint myself into a corner. If you eliminate all the possibilities down to one, no matter how absurd, it must be true. That's not the right word, but that's the idea. Okay, we can express these rate laws like this. And this is called the differential rate law. Notice there's no time variable in here at all. Just the concentration and the order in the constant. And these terms come from calculus. Right. So if you were going for a chemistry degree at a four-year college or university, you probably already have calculus under your belt anyway. But this is the differential rate law. There's also an integrated rate law that incorporates time dependence, and they both are related to one another. But the integrated rate law will have a time variable in there, and one can be inferred from the other. Oops. Too far. There we go. Yeah, the second statement is what I was trying to reference. The differential and the integrated rate laws for a given reaction are related and very well defined, at least for the whole number orders, right? 0, 1s, and 2s. They're the only ones that we're going to study. If you determine one, then you can calculate the other one. So it's a matter of convenience, which one works the best. And we find out that more often than not, the integrated rate law is more useful. Okay. That second step is one that I was talking about earlier. If we know the rate law by experiment, then when we propose mechanisms, the overall rate law will help us eliminate the ones that are not possible. That's nothing new. So now we get to initial rates, method of initial rates. And you want to determine the rate of the reaction as close to 0 as possible. So you shorten the time interval. And it depends on, you'll have some prior knowledge probably of the reaction. So you'll know whether it's a fast or a slow or medium, intermediate. So you'll know how quickly you need to get those first measurements. Right? The one we're going to do in the lab next week is kind of intermediate. Right? We're going to take a blue food dye and we're going to hit it with bleach. And we're going to measure how fast it decolors. Right? That's our measurement of reaction rate. So bleach reacts pretty quick. Right? It's not the fastest of reactions, but it's fast enough where you need to get those measurements at the very beginning quickly. Usually for this method of initial rates, you will have to determine 2 or more experiments. In other words, you set up the conditions such that you conduct the experiment once, then you go back and change the conditions, do it again, and depending on how many reactants you have in the stoichiometry will determine how many reactions you need, how many experiments you need to determine. So if you have something like, let's say we have 3. And it just yields products. So you would have set up an experiment to where you would have a concentration here. Let's say concentration, A1, concentration B1, concentration C1. And and you would have a rate that you would determine from that. And then you would set up, this is experiment 1. Then you set up another experiment where this concentration would be changed. But this concentration would be exactly the same, and this one would be exactly the same. Okay. So you're holding these two constant, let this one vary. And you can use these two. This would be rate 1, this would be rate 2. You would use these two experiments to determine the order for this one, because you're letting this one vary. And you're holding these constant. I'll show you how that works in a minute. But then, how would you get at this one? Well, for experiment 3, then you would hold this one constant. So let's take it back to this concentration. Right? Then you would let this one vary and still hold this one the same. And you get another rate. And I think you probably need one more, right, to get at this one. Let this one vary and hold these two constant. And it can either be 1 and 1 or 2 and 2. Doesn't matter. Okay, that's the idea behind initial rates. These separate experiments, and you're controlling which one you allow to vary. And that allows you to get at the order for this one, and then that one, and that one. Okay. So when we finally write, let's see, this one's only got 2, so let's get rid of that one. And the rate law for this one, the differential rate law, would be some K value. Then you would have the concentration of A, the concentration of B, each one to its own power. Now these orders can be the same, but they're experimentally determined, so you don't know. And this would be the order, this reaction order with respect to A would be N, and with respect to B would be M. But the overall order is simply N plus N. So if that were 1, this is 2, then overall would be 3. Okay. And the effect that it has on the rate is that if this is 1 and you double the concentration of A, what's going to happen to the rate? It'll be double because it's to the first power. But if this is say 2 and you double B, then it's 2 squared. It'd be 4 times the rate. That would be the effect of a change in concentration based upon the order. That one, I get the feeling that happens a lot. Okay, let's leave that there for now. We'll have some examples later. If not today, we'll definitely have some in our review document. Okay, how do exponents in rate laws compare to coefficients in the balanced equations? They're not related whatsoever. They are unrelated in the overall reaction. And here's one 2-sentence explanation, because the balanced chemical equation is an expression of stoichiometry. And that's related to actually end products. It's not what's happening in between. It's what's on either end of the arrow, not what's in between. And that's where the kinetics is happening, on that arrow. It doesn't say anything about the conversion process. Okay. So let's go to representative orders. We're going to see what but we're only going to use one reactant here. It's just for simplicity's sake. Right? If you get two reactants, then you really complicate things. And then three, of course, is even worse. So we're going to stick to just the order for one reactant, like our NO2 reaction. Just one reactant. If it's zero order, that means that the rate is the rate law is K times, and we just use the generic reactant here, to the zero order, right? So that means that the rate is equal to K. And it doesn't matter what the concentration of A is, the rate is always constant. So it's going to be a straight line, the slope, the rate. And if we integrate that rate law, integrated, then we introduce the time factor. So the concentration of A at any time T in our reaction is related to the negative of the K times the time in that reaction, whenever it occurs. And then we just have to know what's the initial concentration. Right? So we can determine the concentration after a certain amount of time. If we know the K and the initial concentration of A, we can calculate the concentration of A at any time, as long as we know it's zero order. Okay. There's one other derived equation that's very useful. It's called half-life. Right? If you've been introduced to radioactivity, you know what half-life is in terms of radioactivity. Right? If you have a radionuclide, any radioactive element, the half-life is how long it takes for the radioactivity to drop by half. Right? Or half of the nuclides have decayed. Well, we can do a chemical half-life also. Well, there's the representation. If you plot using the integrated rate law, let me go back to half-life in a second. Using the integrated rate law, see that's Y equals mx plus b. It's a straight line with a negative slope. So there it is, a negative slope. And the slope is equal to K. But it's a negative K. The y-intercept is A0, and A is any place on that line. So if you plot the data, you have your raw data and you plot, say that NO2, concentration versus time, and it comes out with a negative slope with just the raw data, you know it's zero order. Right? But we saw from the plot, of course, it's not zero order because it was a curve. So we know it's not this one. Let's see. There's half-life. So when we calculate half-life under these conditions, we need to know the initial concentration, and then we need to know K, and we can calculate the half-life. How long does it take for half of that reactant, initial reactant concentration, to be cut in half? Okay. So what this says is, if you increase A, if you double A, then the half-life will double. And if K, if you change the temperature and K changes, then whatever happens to K, if K decreases, then the half-life increases by that factor. Okay. And you don't have to be able to do this. I just put this slide in there so you could see how the half-life was calculated. It was derived from this value, right? And those are the steps that get you to this formula. So I didn't just pull this out of thin air. That's what I'm trying to say. Okay, first order now. Right? In first order, the rate is equal to K, and then A to the first power, so we don't have to write it in. Right, and this is the differential rate law. The integrated rate law then would be, I think it's the natural log of A equals negative K times T plus the natural log of A0. So it's a log function. And this is what it would look like. So if you plot your data, the raw data, right, just concentrations against time, and you don't get a straight line, then maybe the next thing you need to do is take the natural log of A values and plot them against time and see if you get a straight line there. If you get a straight line with a negative slope, then you have a first order equation, first order reaction with respect to A. Okay. And then half-life. Half-life of this one is equal to 0.693 divided by K. So what does that tell you? That tells you that the half-life is independent of the initial concentration of A. Doesn't matter what it is. It's going to take that long for half of it to disappear based upon only the K value. And the value of A doesn't matter. Whatever you start at, it's going to be half of that in the same amount of time, no matter what. Okay, so you could do that. You could calculate you could say, what is the half-life? Look at your data and say, okay, at what point is half of it disappeared? And then take that time interval and use that as your half-life and see if it fits that. Right? We're going to work some of those problems just like that. It does not depend on the concentration of the reactor. And there's your derivation again. Okay. Oh, we're going to have a little problem here. Before we get to second order, we're going to work with first order. A first order reaction is 35% complete at the end of 55 minutes. What's the value of K? Okay, what I do with a problem like this, as always, is I extract information from the word problem and put it in a form that's more recognizable. So I would have concentration of A and time. Okay. So at the end of 55 minutes, so if I start off at 0 and then I go to 55 minutes, what's happening there? Well, the reaction then is 35% complete. Okay, that's the trick. What does that mean, 35% complete? Well, if you start off with a certain concentration here, then 35% of it has disappeared. Right, so what do you have left? Right, we have 65%. Right, you have 0.65 remains. If it's 35% complete, you got that much left over. Okay, that's what that means. Let's see, I think I've got this set up. And we're told it's first order, right? So we can go straight to this one and do calculations based on that. All right. This is a little tricky unless you really, if you're familiar with how logarithms work, you know, remember your rules for logarithms. We're going to start with this one. And what we have is the ratio of the actual value here to its original. And we know that the ratio of this one to this one, right? If we ratio that one to that one, it's 0.65, right? Because the A zeros cancel. So the ratio is 0.65. That's why we rearranged this equation here. Here. so that we got a ratio of A to A0. That ratio is 0.65. So notice that if we get the logs on the same side of the equation, right, log A minus log A0, we just brought log A0 across to the other side. And remember, rules of logarithms, right? If you subtract a log from another log, it's the same thing as the log of one term divided by the other term that was subtracted. That's the transition that's made from here down to here. And we just combine those two logarithms. Now we have a ratio. Okay, then we use the definition of logarithms. Right, so the log of x equals some value y. This is the base e. So what does that mean? That means e to the y equals x. Right? That's definitional for logarithms. So that's where the last step came in. Right, so this is x, and that's the ratio, is equal to e to the minus kt. So that's how far we've come so far. Oops. There we go. So there we have A over A0 is 0.65. Now we know that 0.65 equals e to the minus kt. Well, do we know what t is? Yeah, it's 55. So now we just have to solve that for k. Right? K is in the power of e. So now what we have to do is reconvert that to logarithms. And that's what the next to the last step is. Simple. We just calculate the natural log 0.65 divided by 55, and there's your k. All right. Practice your logarithms. Okay. So let's get on. I think second order is coming up next. Yeah, second order. Yeah, I can do it that way. Second order. Okay, second order says that the rate is equal to k a to the second power. And the integrated rate law, rather than logarithm, is the inverse of a. And A0. Should be back here. I'll do it right. Yeah, that's right. Okay. Notice two things. Not only did the transformation of A change from doing the natural logarithm, instead we take the inverse of the values. And then the next, right, it's kind of like remember Boyle's law? When we took the inverse of volume and plotted against pressure, we got a straight line. We took the inverse here, we got a straight line that's positive. This would be negative, right? The plot of this one, any one of these would be negative, but this one positive with that transformation. There's the original data. Actually, there's not the original data, but this is the log data for this particular reaction. Right? C4H6, which is butylene, I think. And then we plotted it this way and said, no deal, we still got us a curve. So we took the inverse of it, plotted, now we get a straight line. So we know that based upon that, it's a. So that's what you do with your raw data. If you're proficient with Excel, it's better because then you can time against concentration. right? Time against concentration of A here, and you have values here and values here. Then you can go ahead and do like that in this column, right? You know how to say this one equals natural log of this one, right? And then just copy it down. And then you can do inverse. And this one is you just take in your Excel spreadsheet. And then you can go in and chart them, right? Chart this one, build a chart with these two, build a chart with these, see which one is the straight line. And the straight line will tell you what the order is, 0, 1, or 2. And it's safe for this course because I'm not going to throw any odd ones at you. And that's what you'll be doing for the lab too. You'll plot the data, see which one is the straight line, and that'll give you the power for one of the reactants. Right? We got two reactants. We got the blue dye and we got the bleach. So I have to explain how we get around that. And I've got some slides here that we're going to talk about that in a minute. Oh, we need a half-life. Okay. So what's the half-life of this one? Well, I know K is going to be in the denominator. I remember that much. But we also got the initial concentration. And just like that. And I think the second one, this slide is the derivation. So notice one thing about all three of these half-lives. For 0, first, second order, they're all inversely proportional. K's in the denominator of every one. Now, A0 is in the numerator here and in the denominator there, and it's not existent here. But the K is consistent. It's always in the denominator for these half-lives. Okay, so here we have another problem. Let's see. I need a bigger board. If I go to that one. So maybe I can shrink it. Maybe I can shrink 0 order there. Or just erase it and come back to it later. It's probably a better idea. I can write down here. Let's see if I can get it, squeeze it in down here. If we have A to products, so which one are we going to incorporate into the rate law? That one right there. A0 is 5 molar. So we're starting off at 5 molar, right? At time 0. And the first two half-lives are 25 and 50. So half-life means what? Well, after 25, half of that's left, correct? That's the first half-life, so 2.5. Second half-life, though, is 50 minutes. So 50 minutes from here to here is actually 75. And that's half of this one, right there. So that's 1.25. And so there's our data table. Now, we may not need that, but it's true nonetheless. Write the rate law for this reaction. Okay. In the interest of time, write the rate law, calculate the K, then calculate A at 525 minutes. I've got this laid out in slides, so this is going to get us through it quicker so I don't run over. The rate law cannot be first order because of concentration, right? This is a different half-life than that one. And the half-life of this one depends on concentration. The half-life of this one depends on concentration, but that one doesn't. So we can eliminate first order. We don't even have to look at first order. We can't be first order. Then this would be 25 and that would be 50 because the second half-life would be the same. Right? That would be nice if it was that way. Then we'd go straight to first order. But now we've got to decide between 0 and second order. If the rate law were 0 order, then the half-life of A0 would be divided by 2K. Right? If it were this one, then the half-life would be A0 divided by 2K. Well, if we calculate the half-life of this one, right, if we put in 5 here and half-life of 25 here, right, if we put a 5 there and a half-life of 25 here, we can calculate K, right? Right, one unknown, we can solve for it. Do that. And then do it for the second one. Instead of this one, start off with 2.5. And this one becomes 15. Calculate K again. Right? They should be the same. K should be the same. Right? If it's not, then we know that's not it. So that's what the next tables are going to do. Right here. So if we calculate the first half-life at 25, we get K equals 0.1. And we calculate for the second one is 0.025. Right? So we eliminated that one first. We eliminated this one second. So we know it's got to be second order. And we're going to prove it, of course, because we need K anyway. So there's K. 1 divided by 125 is 8 times 10 to the minus 3. So now we know K. We know it's second order, and we know K is that value. So the rate law would be, oops. The rate law would be this K value, plug it right in there. Okay. So if we do that and we calculate A at 525 minutes, then we start off with 5 as our initial. Right? We use the integrated rate law, the second, this one. We put K in here. We put A0 in here. And the time, 525 minutes, is the same units as here. Minutes. Right, so we don't have to change the units of time. Plug those values into our equation, we find out that after 525 minutes, there's only 0.23 molar left out of 5 molar to start with. Okay. I know kinetics is it'll twist your brain around. Okay, so they're all answers to the questions, original questions. Okay, how can you tell the difference between 0 first and second order rate laws from their graphs? We already went through that, but this is to reinforce it. Plot the raw data against time. Plot the natural log data against time. Plot the inverse against time. Which one's the straight line? And that will tell you what order it is. Oops. Oh, it didn't have the answer in black and white. Okay, so what do you do if the rate law on the concentration of 2 reactants? And that's what we're going to face next Thursday. We've got 2 reactants. We've got the blue dye. And this is food color. That's all it is, just food color plus bleach. And that yields products. We're just going to watch the disappearance of the color. So we're going to measure it using a spectrophotometer at a given wavelength, which is the maximum absorbance wavelengths for the blue. So as it decreases, we know that the dye is disappearing. But we're also using up bleach. So we have to account for that too. Well, how do you do that? We've only studied zero first and second order with reference to one reactant. Okay. So here's the way we do it. If there's our rate law, right, we have two reactants with different orders for each one. We increase one of them. In this case, we're going to increase B. We're going to increase bleach to such a concentration that it effectively does not change during the reaction, or the change is so small relative to the other reactants, just doesn't have a significant influence on the initial rate. So we increase B to such a concentration that it doesn't change. It's effectively constant. So we combine that concentration into a new constant. So if we say the rate is equal to A to the N times B to the M times the rate constant, then we say K times B to the M is a new rate constant. We call it the pseudo rate constant. Okay. And now we have a rate law with only one reactant. Right? We can deal with that and determine what is the constant, what is the rate law for blue in our case, or A in this case. Right? That's part of the way there. Okay. Oh, am I going to cut you off with that? Let me see. Yeah, I did. Okay. So we're not going to have time to do an introduction to the lab, but the Brightspace, the course in Brightspace 104 has a couple, actually has 3 recorded discussions, and they should give you good background. I'd go to the one that was recorded in February, I believe it was, the spring semester. It'd probably be the better quality video. And there will be a complete discussion of what we do here. But I'll say in short, what we do is we calculate the pseudo rate constant given concentration of bleach, and then we'll go back and do the experiment all over again with half the concentration of that bleach. And we find out this is the full strength pseudo rate constant, and then we determine a half strength pseudo rate constant. And once we've determined what this one is, based upon our whether it's zero first or second order, then not that one. That's not up there. We determine this one for each of these. They, in fact, should be the same. Then we can ratio those and find out what this one is. Okay, it's sort of a modified initial rates approach. The method itself has, I believe, it has a discussion. If you could follow it. There's the method. Oh, here we go. Yeah, there's a discussion. And here's how we calculate the bleach concentration. You have to know that also. Got to be able to calculate the bleach concentration. There. This one and kinetics experiment and formation constant. Those two give us students the most trouble from first or second semester. And so don't be dismayed, just plug away at it. And if you have questions, that's what I'm here for. Okay, so this table just has all of this information that we covered earlier in one location. And that comes out of your book too. All right, let me see how far along I am. If I need to speed it up any. I need to get to mechanisms. Okay, so this one's worked out. I don't have to write this one on the board. For this reaction, where we have initial concentration is 5 molar, and K equals 1 times 10 to the minus 2. Notice there are no units there. We're going to talk about this a little later with respect to equilibrium. We generally don't incorporate the units because there's so many possibilities. It just, the sky's the limit. So you just have to be careful with your calculations. Calculate A after 30 seconds have passed. Assume the reaction is 0 first or second order, right? So if it were 0 order, right, that would be our integrated rate law. And we're given values, we're given time, we're given K, we're given initial rate. We calculate A equals 4.7 molar after 30 seconds. If it were 0 order. If it were first order, we just do the same thing with the integrated first order rate law and plug in the values and find that if it's first order though, the final concentration is 3.7. So that makes sense, right? If it's 0 order, if it's first order, it's moving faster. If it's second order, it should be even lower. And it is 2 molar. So under those conditions, depending on whether it's 0 first or second order, gives us a different value for the final concentration. Okay, so if we have this initial rates data for a reaction, for this reaction, and I know it looks complicated, but you got the manganate ion plus oxalic acid, I think, and then extra hydrogen ions, and then that the products are the manganese 2, carbon dioxide, and water. Then we want to have determined initial rates for manganate, oxalic acid, and free acids. And this is what we get, these 4 experiments, just like I drew earlier. We have 3 reactants, so we need 4 experiments to cover all the possibilities. Right? And notice that for this one, if we go from the first experiment to the second one, I should have put labeled them out here, first, second, third, fourth. Then this one changes and these 2 don't. So we can use these first 2 to determine the order for manganate ion. For the second one, we can say, okay, manganate's constant here and hydrogen constant here. We can use 2 and 3 to do the oxalic acid. And then these 2 are constant, these 2 constant here, and we can use the third and the fourth one to do the hydrogen ions. Okay. Oh, all right. It's going to make me do it. Yes, I should. All right. I'll just have to move along at a pretty quick clip. I'm going to use this data. So, and I find it convenient to write out the reaction here. Here it is, to write out the reaction and then put the values, right, the concentrations underneath each one. So they would line up here. These would line up here, these would line up here, and then put the rate up there. Then I only have to write these down once. Okay, so for the first one, what we have is the manganate. We want to do the manganate first. So what we're going to have is the first experiment and the second experiment. And if we write the rate here, the rate here, and ratio them, then the rate here and here, and I'm going to use the second experiment first, and then the first experiment second. Why would I do that? Because the rate for the second one is greater than the one for the first one. And that gives me a whole number rather than a fraction. Okay. So the ratio doesn't matter, but it makes it a little simpler if you look ahead and say, okay, so for this one, we're going to have, what's the rate law here? Well, the rate law is going to be MnO4 minus to the n power, and then H2, excuse me, H2 C2O4 to the m power, and then hydrogen ions to the O power. Well, I shouldn't do O. That could be a mistake. To the P power. Okay. And that rate is, the first one is 8 times 10 to the minus 4. Okay. The second one will be the same values. This will be P, this will be M, this will be N. And we'll substitute in here 2 times 10 to the minus 4. Okay. So we just have to put values in here. Right. This one's going to be 2 times 10 to the minus 3, isn't it? So we put that one in here. 2 times 10 to the minus 3. And then 1 times 10 to the minus 3 for this one. And this one is 1. 1 and 1. And this one should also be 10 to the minus 3. 1 times 10 to the minus 3. And this one is 1 times 10 to the minus 3. Right? Okay. Notice that this is the same as that one. This is the same as that one. So we have a ratio here, which is equal to 2, isn't it? To the n. Okay. And what's this one? 2 into 8 is 4. 2 times 10 to the minus 4 into 8 times 10 to the minus 4 is 4. Okay. So what power of 2 gives you 4? 2. So for this one, this is 2. Let's do C2O4. And we haven't done this one yet. We haven't done that one. Okay. But we do the same thing for each one. Just pick the experiments where you can hold all constant except for 1. Right. So for the second one, we're going to hold this one constant and that one constant. Right. So that one gives something, that one gives something, that one something, that one something. They're the same. This is the only one that varies. So the high one is this one's third, this one's second. So the third one is 1.6 times 10 to the minus 3. 6 times 10 to the minus 3. and this one is 8 times 10 to the minus 4. And the values here would be 2 times 10 to the minus 3, and this one's 1 times 10 to the minus 3, right? Okay, so we know that these cancel, and this one gives us a ratio of 2, right? 2 to the m. And this ratio is, well, why don't we make this one minus 4? How would you do that? All right, make this one smaller, that one's got to get bigger, right? 0.16. By the way. Yeah. If we take this, increase this one, then that one's got to decrease to 1.6. So if we go up to minus 3, this one comes down to 1.6. We go 1.6, increase that to 16. This one has to store that extra decimal. Okay. So that becomes 2. And if your mind is swimming during the test, just put it in your calculator. So m would be what? 1. Okay, so now we know this one. All right. So this one's going to be held constant. This one's going to be constant. This one's going to change. So for these two constants, which ones are those? 4 and 3, right? 4th and 3rd. So the 4th one, actually, these are going to change also. So the 4th one would be 1.6 times 10 to the minus 6, 10 to the minus 3, 1.6 times 10 to the minus 3. And this one would be 2 and 1. So this would be 2 to the p power equals 1. So what power of any number gives you 1? Yeah, 0. P equals 0. So now we know that happens 0. Okay. Now, how do we get to K? Right. The rate law is going to be K times that value. Pick any experiment, any one, and say the rate. We'll just pick the first one. The rate is 2 times 10 to the minus 4. And that's equal to 1 times 10 to the minus 3 squared, and 1 times 10 to the minus 3 to the first power. And this one's to the 0 power, so it's 1. And left out the K. Solve for the K. That one times that one divided into this one gives you K. And in the interest of time, K is 2 times 10 to the 5th. And the rate law, since this is 1, you don't have to write that term. So the only terms that are in there are this second order and this first order. Okay? That's the method of initial rates. I know it takes a lot of time to do, but that's the nature of the beast. All right. That ate up a good 10 minutes. Okay. Now to reaction mechanisms. Most chemical reactions occur in a series of elementary steps. There are reactions that only have one step. But there are also reactions that have 2 steps and a few that have 3 steps. Right, and what they do is, on this arrow, you can have reactants, and they don't have to all be this. You don't have to have A, B, and C. You can just have A and B. It'll give you 1 step. And then the product of that will be an intermediate that you don't see in the overall. Could react with C. Right? Or if it's 3-step, It could react with B, and then that product react with C. The sky's the limit, right? You could have several steps in here. Right. This is where the mechanism occurs, right here on that arrow. Right. Here's an example where you have two steps. Now this one's confirmed. Right. This mechanism is confirmed, so I'm not feeding you a line. Step one, you've got NO2. Two of the NO2s react, and they produce an NO3 and an NO. Then this NO3, so you got your NO already. That's right there. This NO3 then reacts with carbon monoxide, and it regenerates an NO2 and a carbon dioxide. Right. So overall, and this is the first rule of a mechanism, you have to be able to add the steps together and get the overall equation. And it's like Hence's law. You add them all together, and you get the overall equation. Notice that when we do that, this extra NO2 that isn't in here, right? We only got one of them there, right? This extra NO2 is canceled by this one because it's recreated in the process. But this NO3 is not in the overall equation. It's an intermediate. So it's created here and it's used up over here. That's an intermediate. Okay. Now, these individual steps can be classified depending upon how many reactants must come together to create one of those elementary steps. If it's unimolecular, then it's like that NO2. It just decomposes. It doesn't need any help. It's unimolecular. If you have two that have to come together, then it's bimolecular, which is the example we just showed you. Those elementary steps, both of them were bimolecular. Now, what's the probability of bimolecular relative to unimolecular? The probability of bimolecular is less, as a general rule, than unimolecular, because you've got to get those two players together at the right energy and the right orientation so that their reaction will occur. And that's the probability of that is much less than it is if you only got one player that just has to go. Termolecular is even worse, where you have three players that have to come together exactly the right. So these steps are very rare. Termolecular steps where you have three players in an elementary step. They're very rare, and we only use them when nothing else works. All right. Also, when you have these steps, step one, let's say we have three steps. And each one has its own rate, right? It has its own rate equation. The overall rate of the reaction is determined by the slowest one. That's the rate determining step. Now, they could all be very fast, but one of them is slower than the others. And that would be, say, if this is the slowest step, this would be the rate determining step. And the nice thing about that is, if you know the overall rate of the reaction, it's dependent upon that one. So that tells you that the overall rate is that rate. Okay. Okay, did I skip something? Let me see. Yeah. The overall rate law has to be experimentally determined, but the rate law for each one of these can be determined by the stoichiometry of the step. We already did this slide, didn't we? I got it duplicated. This is also called molecularity. That's a funny word. Reminds me of MASH. Have you seen the old MASH episodes? Father Mulcahy, when everybody was just raising a riot, his term for it was jocularity. That always flashes back in my head when I see this. Molecularity. It's funny. We already done this. Am I going?
He's went the wrong way there.
I did go the wrong way. Yeah. Yeah. There you go. Okay. First of all, like I said before, the sum of the elementary steps must equal the overall equation. That's the first. Then the mechanism must agree with the experimentally determined rate law. And so if the mechanism gives you a different answer for the overall rate law than the experimentally determined rate law, then you can throw that mechanism out. All right. So here we have the decomposition of dinitrogen pentoxide into 4 NO2s and an O2. We've got a fast step, a slow step, and another fast step. So the slow step 2 is the rate determining step. The first step is unimolecular, right? N2O5 just decomposes it into NO2 and NO3. And then NO2 and NO3 react and produce, that's a bimolecular, produces NO, O2, and NO2. And then another bimolecular where NO3 reacts with NO. NO is an intermediate. Notice NO doesn't appear anywhere in this equation. So NO, actually NO3 is an intermediate also. So NO3 is used up here, producing NO, but NO is then used up here to give you 2 NO2s. Now, first of all, can we add these together and end up with the balanced overall equation? Well, the NO3s cancel, the NOs cancel. We've got N2O5 let me see. Oh, okay. So I've got an animation here. There we go. So in order to add them together, we go back to Hess's law. And we manipulate the equations, right? So they'll add together properly. And if we multiply 2 times step 1, then that gets rid of 2 NO3s on the left and 2 NO3s on the right. That's good. And then the NO2s cancel out of the second step. And the NOs cancel out of the second, third step. And doesn't show it, but 2 N2O5s here, there. And then 4 NO2s. Do we have 4 NO2s? There's 2 there. Yep. So we're good there. And then the O2, we have 1 of them here. Okay. So it met that condition. The first condition. We didn't deal with the second condition yet. This reaction, A plus 2B yields C. Okay. Let me check this out here. Oh, good. Right. I do have subsequent slides that put this one together. So we've got a proposed mechanism of a fast equilibrium. Now, we haven't talked about equilibrium yet, but when we write equilibriums, we put a double-headed arrow. That means the reaction goes both directions, and it happens really fast. And then the slow step, the rate determining step, is this one. This one's slow, that's rate determining. So if we can write a rate law for this step, and then somehow get rid of that D, right? Because there's no D up here. Right? So if we write a rate law for this one, then we got to get rid of that D somehow. All right, so the first thing I want to do is say, well, does it meet the first condition? The D's cancel. You got an A here, you got two B's here, and you got a C there. So yeah, it meets the first condition. So what we're doing here is we're identifying the rates. So this one has a rate constant for that direction. It also has a rate constant for the reverse direction. And then this one has a rate constant for that direction. Since it's slow, it only goes in one direction. We only have to deal with one direction. Okay. So since the rate determining step is a slow step, then the rate that we can write for this one is the value of D. Since there's only one of them, then it's to the first power. And then we have K2, which is the rate constant for that one. And then times B, also to the first power. So that would be the rate law for this elementary step. Now we got to figure out how to get rid of D. All right. So we take the fast equilibrium, where the forward and reverse reactions are equal. So we write a rate expression for the forward reaction, we write a rate expression for the reverse reaction, and set them equal to each other. Because it's a fast equilibrium, their rates should be equal. So there's the front one. A to the first power, B to the first power, and K1. That's also equal to the reverse reaction, which is D to the first power with K to the minus 1. And then we solve for D, and that gives us a substitution for this one right here. So this becomes K2, and then the substitution is K1 over K minus 1. And then we substitute for D, which is A B. And then B is still out here, right here. And this one is this one and those two. So now we just have to reduce it. So the overall rate law then this one, these are elementary step rate constants, and they all equal the overall rate constant, K. Then we have A here, and we have B squared. Right, so that's your overall rate law based upon these elementary steps. Now, we did that mathematically. What we have to do now is compare this to the experimentally determined rate law. Right? And does it have the same orders, the experimentally determined rate law? Does it have the first order for A and second order for B? And the K that we determined from these steps would have to be equal to the these values in here. Now that's a little more problematic because I don't know how to determine these on elementary steps because they're happening in mystery right here. So I assume that we would just say, well, if the orders are correct, then our elementary steps are probably correct. All right. So now, up to this point, we've talked about experimentally determining the rate laws, right? We're not trying to explain why things happen. We sort of inferred with our elementary steps that that the rate law itself is determined by some sort of explainable mechanism, right? A theory. And this is the theory that we're using, the collision model. The first condition is that the molecules have to collide. They must bang into each other in order for a reaction to occur. The next main factor is that they have to have enough energy when they collide. And that's called the activation energy, E sub A. Right? And that can be dependent upon temperature, or if the molecules absorb ultraviolet light, which sometimes they do, you can provide energy that way. But they have to have enough energy when they collide in order for the reaction to occur. It has to exceed the activation energy. I'm going to draw you a graph here in a second. So that could be temperature, could be some other factors. Then they also have to be oriented properly. Right? If the reaction sites are on this side of the molecules and they come together like that, nothing's going to happen no matter how hard they hit. Right? They've got to be oriented correctly. That's why the termomolecular is so rare, because orienting three molecules coming together at exactly the right orientation and energy is very rare. It's difficult to obtain. So this activation energy, we would draw it like this. So this is reaction progress, they usually say. It could be any time scale. It's not important. But this is energy. And this is the energy of any of the reactants and products or intermediates. So if we start off down here, let's say, we start off here with reactants. So this is the combined energy of all the reactants here. And we have to add energy to them. So if we add energy, during their collision, they come together, and if they exceed just a little bit that activation energy, then they can go down the other side and make products. The measurement from here to here, that's the activation energy. Okay, that's the minimum amount of energy required for the reaction to proceed. And what you'll have up here is sometimes it's called a transition state or an activated complex. Or activated complex. Okay. And actually, since this is overall, then what happens in here, there could be multiple steps all the way to that one, right? Those elementary steps could occur in here. But we're trying to take the big picture now. So the difference between this energy and this energy is the enthalpy of the reaction. Okay? So if this one has more energy, this one, the products have less energy, this enthalpy is going to be negative, exothermic. Okay. So just as a lead up to chapter 13, kinetics happens in here. That's where all the rate happens. Everything else is equilibrium. Right? It's overall. We start here, we end there. Who cares what happens in between? Right? Okay. That just restates the obvious. All right. This fellow, Svante Arrhenius, he was a Swedish chemist in the middle 19th century, I think. And he proposed this equation that related temperature, the rate constant, and activation energy. And that you see that R in there, that's your gas constant. And it's going to be the one with joules, 8.3145, I think. Now, while that equation is true, and the various factors in here, like the A, frequency factor, which is a product of collision frequency and orientation effect. is not very useful for doing calculations. Right? So we need a better approach. Right? This is true, right? There's nothing wrong with that equation, except that we don't know what A is. E, of course, is the base for natural logarithms. So we rearrange the equation, right? And you can do that, right? From that equation, you just take the natural log of the whole thing and then reduce it. And you get a straight line expression, right? Y equals M X plus B. Okay, so if you plot the natural log of the K values, and this requires 2 or more experiments at different temperatures. Okay, so a minimum of 2 will give you 2 points on that straight line. Okay. So you determine the K for that temperature. And if you plot the natural log of the K against the temperature for that K and a series and plot them, the slope will be negative activation energy divided by R. And the y-intercept will be natural log of A. So you can determine A from this also. All right, so here's our example. So we did 1, 2, 3, 4, 5 experiments, different temperatures. We took the inverse of the Kelvin temperature and plotted against the natural log of the K values that were determined at each one of those temperatures. And that slope then is this term right here. It's a negative E sub A over R. We know what R is, so we can calculate E sub A. We can determine the activation energy based upon this plot. All right. I'm already over time. Let me see how much more. Catalysts. I'm going to let you read the catalysts. There's not much. We'll go through it really quick. What must be the, all right. Actually, we can skip this one. All I'm doing here in this next series of slides is proving, well, actually not proving, but calculating what must be the activation energy to satisfy the rule of thumb. I heard this from high school. The rule of thumb for chemical reactions. And of course, initially I was studying to be a biologist, so it was biochemical reactions. The rule of thumb is that the reaction rate is proportional to let's see, that's not really right. The reaction, let me just put it in words. The reaction rate doubles for every 10 degrees Celsius increase. So if your temperature goes from 20 degrees to 30 degrees, the reaction rate will double. But that's a rule of thumb, all right? It can vary all over the place. What I did here was to say, all right, if I double the temperature, or if the temperature goes from 25 degrees to 35 degrees, what would have to be the activation energy in order for that rule of thumb to be valid? And so that's what happens for each one of these, and it looks like a mess right there, right? So what to make a long story short, I said I had to calculate the temperatures in K first, and then I took this equation, the Arrhenius equation, say, okay, that first K would be this at that temperature, and the second K would be this at that temperature. But this K would have to double in order for this to be valid. So actually, this expression is equal to 2 times the first K. So we ratio the 2, and then we ratio their equivalents, and then we just follow the calculation all the way down and determine the E sub A. And the E sub A would have to be 52.9 kilojoules in order for that rule of thumb to work between 25 and 35 degrees. All right. And I'll leave it up there long enough to get a good recording, and then we'll move on. Catalysts. All right. We should be able to finish by 11:30. Actually, I shouldn't have erased that. Let me put that back up here. Reaction progress. Go like this and like that. So this is the E sub A for an uncatalyzed reaction. In other words, nothing helping it. What is a catalyst? A catalyst is any substance that causes the rate of the reaction to increase. And while it participates in the reaction, it is unchanged by the reaction. In other words, it comes in, catalyst comes in one end, goes out the other end, and for the overall stoichiometry, it doesn't change. So that's why when we write reactions, we usually put the catalyst here. Right? Because that's where it's active. It's active on that arrow. It's not active here, it's not active there. It's active in the mechanism, in the elementary steps. Okay. What it does is it provides an alternate mechanism for the reaction, different elementary steps that happen faster. And the overall effect is that with a catalyst, that activation energy is lowered. So it does have its effect in here, in the kinetic region. There you go. Notice that the overall energies are not changed from the reactants and products. In other words, that delta H is the same whether we have a catalyst or not. It's just with a catalyst, it gets there quicker. Right? All right, this is another explanation for what happens. If the y-axis is the number of collisions with a given amount of energy, you find that there's sort of a, that's not a normal distribution. It's more like a chi-square distribution. Anyway, you only have uncatalyzed reaction. You only have this many collisions, the area under that curve. That's the number of collisions that have sufficient energy uncatalyzed. With a catalyzed, we increase the number of collisions that can produce a reaction because we provide a different mechanism with a lower activation energy required. That's what catalysts do. They change the activation energy for the reaction. All right. If the catalyst is in a different phase than the reactants, then it's a heterogeneous catalyst. The best example I can think of is your catalytic converter in the car. Right? You've got gases coming through catalytic converter. The catalyst is platinum and palladium plated on a ceramic matrix. Right? There's in the solid phase, the reactants are in the gaseous phase. That's a heterogeneous catalyst in that ceramic matrix. They used to be beads. That's ceramic beads coated with platinum and palladium. But shade tree mechanics quickly figured out all you had to do was take a screwdriver and out come the beads. And then you just seal it over and you got a car that runs with the power it had before they put the catalytic converter on it. So they switched to a solid matrix catalyst, solid matrix of ceramics, and then coated those with, and now you can't do that anymore. So it's like an arms race, right? We produce a superior weapon, and the enemy finds a way to counteract it. So we make a better weapon, and they just back and forth. Okay, so with heterogeneous catalysts, very often the reactants are adsorbed to the surface in some form or fashion. And these are the steps that would occur. The reactants are absorbed and activated on the surface of the catalyst. So you would have your ceramic matrix and your platinum and palladium here. And then your reactants would come in. This gas would be here, and this gas would be here, and they would be activated by those, and they would actually migrate toward each other on the surface of the catalyst. And they would be, that would guarantee their orientation was correct also. And then once the reaction is complete, then they desorb and out your tailpipe. Oh, there's a artist rendition. Homogeneous catalysts, on the other hand, are those in which the catalyst and the reactants are in the same phase. The best example I can think of that one is hydrogen peroxide. You have 30% hydrogen peroxide, and you have potassium iodide dissolved in solution, and you pour it in there. And the reaction occurs so fast that you get this huge froth coming out of it, right? The hydrogen peroxide is decomposing into water and oxygen. And both the catalyst and the hydrogen peroxide are in the same phase. They're both liquids. I think I have well, this also happens in cells. Right? Enzymes are biological catalysts. Right? That's an oversimplified version. Enzymes are far, far more complex than inorganic catalysts. Enzymes usually catalyze reactions in one direction only, whereas inorganic catalysts will go both directions. What that allows the enzyme to do is control. It says that enzyme will catalyze the reaction in one direction. Once it gets there, it can't come back. In order to come back, it needs a different enzyme. Now, there are some examples, some exceptions to that rule. One is problematic, but we don't have time to go into it right now.
Try yours. So that's the technique. Just dump it right in and see what happens.
Oh wow. Okay.
Okay. So
whoa,
we're releasing
okay.
lots and lots of oxygen gas. Okay. So why don't you go ahead and do yours now? Yours is a little bit different container. It's got, just dump it in really quick.
Okay.
Perfect. Yours is like more. And you just generate tons and tons of oxygen. It's being trapped by the soap, okay? It's like a supersized version of what kind of happens when you pour it on your body.
Sure.
Where that catalase enzyme breaks it down.
But again, we're not actually cleaning anything, if you will.
Technically, the hydrogen peroxide, when it generates this oxygen, can kind of dislodge big hunks of stuff.
This is like more of a...
In order to make it do that, they put a little dish soap in it and food coloring. I had a student at Logan several years ago. He and his, I think she was his girlfriend, they were expecting a child, and they wanted to do a gender reveal party. So he used this approach, and he put, I forget, blue or red, depending on the gender, for the reveal. That would be cool. He got it wrong the first time. They did another ultrasound and found, oops, wrong sex. So he was fine with that because they had to do it again. Yeah. Okay. So this is the mechanism for that reaction. It's got 4 steps. And the slow step is that first one, to produce oxygen with iodine as a catalyst. Potassium iodide was in solution. The woman poured it into her Erlenmeyer flask. And this is the reaction that occurred. All right, there are other types of reactions. Some of the most problematic ones are the ones that occur in our upper atmosphere with ozone. Right? When we produce nitric oxide, NO, as a product of internal combustion engines, it works its way to the upper atmosphere and destroys ozone by this catalytic reaction. And because NO is a catalyst, notice that NO is a homogeneous catalyst, and the mechanism says see, where's my arrow? There it is. The mechanism said it comes in this side and it goes out that side. And so it's unchanged. That is a key to catalyst. If it were an intermediate, it would be produced on the right-hand side and then consumed on the left-hand side. But as catalyst comes in, you can see it going in and you can see it coming out. This also happens with certain freons, refrigerants. The original Freon 12 was a difluoride of methane, substituted methane. And it was very good at decomposing into this gas, right? Normally, chlorine is diatomic, right? At room temperature and at 1 atmosphere pressure. But in those upper atmospheres, it decomposes into atomic. And the thing to notice here is paired, 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 unpaired. This is a free radical. They are extremely reactive. And it goes and reacts with ozone and destroys it as a catalyst. And the bad part about it is, since it's a catalyst, once it destroys one ozone, it can go over and kick out another one and just keep going. Okay, so now we have to have substitutes for Freon 12, which are more expensive. And if you've got an old vehicle with an early air conditioning system in it, try to get Freon 12 for it. You're going to pay through the nose if you can find it. So a lot of people they just rip those out and put a new one in. It's cheaper. Okay. Any questions?
You said that lab is going to be next Thursday?
Yes, this coming Thursday, day after tomorrow.
Okay, that's.
Yep.
Okay, this Thursday.
Yeah.
Okay.
And the best thing for you to do is watch the video. You can fill out your notebook from the hard copy and put places in your data pages where you know you're going to need information. And then how to treat it is covered largely in those videos. And then also on that day, we'll have a review.
Okay.
Yep. Do the review and then we'll go in the lab.
Okay.
The lab doesn't take very long. It's the aftershock. That's the problem. You have to deal with, what do you do with these numbers? Yeah.
Yeah.
But it's pretty cool.